Section: Introduction. In this section, we will discuss how transformers have become more popular than recurrent neural networks, RNNs, for sequence modeling tasks due to their efficient parallel training and excellent scalability. However, transformers have a drawback of higher inference cost compared to RNNs, as the cost increases linearly with the number of tokens. This has sparked interest in combining the benefits of transformers and RNNs to reduce inference costs for language and multimodal models. Recent studies have shown a connection between a linearized form of attention and recurrence, blurring the line between transformers and RNNs. This allows models to be trained like transformers but operate like RNNs during inference. While some new RNN architectures have tried to bridge the performance gap with transformers, such as RWKV, retentive networks, transnormer, Griffin, and recurrent gemma, softmax transformers still outperform them in natural language understanding tasks. State space models, SSMs, offer another alternative to softmax transformers by combining RNNs and convolutional networks to model long sequences efficiently. The Mamba architecture, a type of SSM, has shown impressive performance on smaller scales, matching or even surpassing softmax transformers on various natural language understanding benchmarks. However, for tasks requiring long context understanding, softmax attention still holds an advantage. Instead of pre-training linear models, one approach is to convert existing transformers into RNNs by introducing an approximating MLP attention module. While this method shows promise, it can lead to instability and poor performance when uptraining large-scale models. Our approach, called Scalable UP Training for Recurrent Attention, SUPRA, takes a different route by replacing softmax attention with a linear kernel and a normalization strategy to uptrain high-performing large language models, LLMs, into RNNs. By fine-tuning these models on publicly available data after pre-training on massive proprietary datasets like Mistral and Llama 2, we achieve competitive performance with the best linear transformers using less computational resources. Our contributions include proposing SUPRA as a strategy to uptrain state-of-the-art LLMs into efficient RNNs, demonstrating its competitiveness with pre-trained recurrent LLMs, and exploring the limitations of recurrent LLMs compared to transformers in in-context learning and long-context tasks. Moving on to the methodology, we will review linear transformers, explain the linearization technique that underpins our approach, and introduce SUPRA as our method for uptraining large transformers into RNNs. In the background section on linear attention, linear transformers establish a link between transformers and RNNs by replacing the softmax dot-product attention with a more general similarity function between queries and keys. The authors explore various functions for this similarity, including a linear kernel, and show the computational advantages of linear attention. They also demonstrate how this model can be represented as an RNN, especially with attention involving causal masking. Linear attention can be seen as an RNN that updates a state and a normalization factor at each time step, known as the attention memory and normalized memory. This RNN formulation is equivalent to linear attention, allowing flexibility in choosing the most suitable one for a given task and hardware. During inference, the state acts as a constant size cache for key value pairs, ensuring a constant inference cost regardless of the number of generated tokens. Section Summary. In this section, we introduce the shift from recurrent neural networks, RNNs, to transformers in sequence modeling due to their parallel training efficiency, though transformers incur higher inference costs compared to RNNs. Recent works have explored a duality between transformers and RNNs, leading to the development of novel RNN architectures like RWKV and transnormer, aiming to bridge the performance gap with transformers. Our approach, Scalable UP Training for Recurrent Attention, SUPRA, proposes a linearization strategy to uptrain advanced language models, LLMs, into efficient RNNs, showcasing competitive performance with pre-trained recurrent LLMs and highlighting persistent gaps in long context tasks. Section: Fine-tuning a transformer into an RNN. In this section, we introduced a method called T2R that converts a pre-trained softmax transformer into an RNN by approximating the attention computation with multi-layer perceptrons, MLPs. We start with a softmax attention model and linearize the softmax operation. Instead of using a simple non-linearity, we employ a trainable layer with shared weights between keys and queries for a given attention head. By rearranging the operations, attention can be expressed differently to enable recurrent inference. However, this approach has some drawbacks. It requires significant retraining of the model, using around 20% of pre-training tokens for conversion, and experiences a drop in performance of 5 to 10% on language benchmarks. Additionally, this method was tested on relatively small models around the 100 million scale, leading to stability issues at larger scales due to closely mimicking the attention formulation. To address these issues, we modified the approach to suit large-scale model uptraining with SUPRA, scalable UP training for recurrent attention. Instead of training linear models from scratch, we opt to uptrain state-of-the-art transformers using a fraction of pre-training data. We build on T2R, identify key issues, and propose SUPRA as an approach to fine-tune very large transformers into RNNs. We address the instability of the normalization factor in linear attention by replacing it with group norm. We also highlight the importance of using modern relative positional encoding schemes like ROPE for competitive performance. By incorporating these findings and using MLP kernels, we convert large language models into RNNs. The attention formulation is adjusted by adding shared weights between keys and queries, applying a specific function, and utilizing rotary positional embedding, ROPE, for similarity calculations. During training, these new parameters are optimized alongside the rest of the network, while at test time, we employ the recurrent formulation for inference. We conducted experiments by uptraining various models ranging from 1B to 7B into RNNs, Llama 2 and Mistral, and evaluating them on standard language understanding benchmarks and long context tasks. Our results demonstrate the limitations of linear models compared to recurrent models on various benchmarks, showcasing a persistent gap between vanilla attention and recurrence. Section Summary. In this section, we introduce a method called T2R that converts pre-trained softmax transformers into RNNs by approximating attention computation with multi-layer perceptrons. However, this approach requires significant retraining and may lead to a drop in performance on language benchmarks. To address these issues, we propose SUPRA, a method that fine-tunes large transformers into RNNs by linearizing them using a fraction of pre-training data and incorporating modern positional encoding schemes for improved performance on long context tasks. Section: Decay Factors. In this section, we discuss decay factors and ablations in our study. We found that default decay factors work better than no decay for short context tasks, but for long-range tasks, the decay can diminish the impact of context. This behavior is similar to a smoother version of window attention. When we provide more context to the model, the performance for long-range tasks levels off. Using values that allow for longer range attention leads to a drop in performance for short context tasks and no significant improvement for long context tasks. Next, we compare transformers pre-trained on 100 billion tokens to Mamba, T2R, and our approach. The Mamba model performs the best at this scale, with the other models showing similar performance. When uptraining from a pre-trained transformer, we observed that T2R uptraining was unstable and yielded poor results compared to SUPRA, highlighting the importance of normalization for maintaining performance during uptraining. To test if linear attention can approximate softmax attention, we conducted a two-step experiment. The results showed no benefit from the two-step approach, indicating that linear attention does not approximate softmax attention. Additionally, we compared the results of uptrainings from two pre-trained models and found that pre-training a linear model with 100 billion tokens yields better results than fine-tuning a softmax model with the same budget. In our discussion, we compare our approach to pre-training SSMs, RNNs, and transformers on short context tasks. While our approach does not explicitly approximate attention from the base transformer model, we observed a modest drop in performance compared to softmax transformers across all benchmarks. Linear transformers may be inherently less expressive, but the performance drop is relatively small compared to other uptraining methods like T2R. When comparing long context tasks, we found that linear models generally maintain performance beyond their training context, while transformers do not. However, simple linear scaling of positional embeddings in transformers can allow for context scaling beyond the training window, negating the performance advantage of linear models. Transformers tend to outperform linear models at their maximum training context length. It is important to note that our method relies on strong pre-trained transformers, which may inherit biases and weaknesses from their base models. Additionally, our models may struggle with in-context learning tasks and may not linearize as effectively as base models. Future research is needed to address these limitations and further explore the potential of linear models in long-context inference tasks. Section Summary. In this section, we explore the impact of decay factors on context influence in transformer models, finding that default decay factors perform better on short context benchmarks but plateau long-range evaluation performances. A comparison of transformers pre-trained on 100B tokens to Mamba, T2R, and a new approach shows that Mamba performs best at this scale, emphasizing the importance of normalization for maintaining performance during uptraining. Additionally, our experiments suggest that linear attention does not effectively approximate softmax attention, and pre-training a linear model from a strong transformer yields better results than fine-tuning a softmax model with the same budget. Section: State Space Models. In this section, we discuss state space models, SSMs, like H3, Hyena, and Mamba, which are newer options compared to traditional transformers. These models blend the strengths of convolutional and recurrent models and are efficient for hardware use. Instead of training sequences in parallel, they offer a more effective way to train sequential RNNs. Although SSMs perform well on certain tasks, they also face similar limitations as linear transformers on tasks involving in-context learning and long contexts. Moving on to uptraining linear transformers, Hedgehog expands on previous work by exploring 3 methods for training linear transformers, starting from scratch: uptraining quadratic transformers for specific tasks, and general uptraining. While the authors focus on the first 2 methods, we concentrate on the third approach. Their goal is to approximate softmax attention matrices with linear alternatives. However, our approach differs as we replace softmax attention with a linear alternative, as detailed in the ablation study in Appendix. The method proposed by the authors is tested on smaller models and involves parameter-efficient fine-tuning for larger models. However, it poses challenges for scaling due to 2 main reasons. Firstly, their training approach requires comparing full attention matrices, which is computationally intensive and impractical for fully fine-tuning large models with long sequences. Secondly, their method inherits gradient instabilities from linear transformers, whereas our normalization technique ensures stable uptraining of large models.